Picture this. Right now, 7 billion years worth of frozen history is racing toward Jupiter at speeds that would make your head spin. And when these two cosmic giants meet in just a few months, something's gonna happen that's never been recorded in human history. What I'm about to tell you isn't science fiction. This is actually happening right above your head as you listen to this. A visitor from another solar system, one that died before Earth even existed, is about to brush past the largest planet in our neighborhood. And the consequences? Nobody really knows for sure. But here's what we do know. And trust me, it's going to change how you think about the universe. See, most people think space is empty, just darkness and silence stretching forever. But that's not true at all. Space is actually crowded with ancient messengers carrying secrets. We're only just learning to read. And one of these messengers just showed up at our doorstep with a story that's been traveling for longer than life has existed on Earth. Its name is 3I divided by Atlas. And it's not like anything we've seen before. Let me take you back to July 2025. Astronomers were doing their usual work, scanning the sky, cataloging objects, when something unusual caught their attention. At first, it looked like just another comet, but the numbers didn't add up. The trajectory was all wrong. The speed was impossible for something that belonged here. And then they realized what they were looking at. This wasn't from our solar system at all. This was an intruder. A wanderer, something that had been drifting through the galaxy since before our sun was born. Now, before 3I divided by Atlas, we'd only seen 2 other interstellar objects pass through our neighborhood. You might remember them. There was Oumuamua back in 2017, that weird cigar-shaped thing that some people thought might be an alien spacecraft. Then there was Borisov in 2019, which looked more like a normal comet but came from somewhere else. But 3I divided by Atlas? This thing is different in ways that are making scientists nervous and excited at the same time. First off, it's massive. Way bigger than anyone expected. When they first spotted it, they thought it was maybe a kilometer across. Standard comet size, nothing special. But as they kept watching and taking more measurements, they had to revise that number, then revise it again. This thing might be several kilometers wide. It's not just a snowball. It's a mountain of ice and rock that's been traveling through interstellar space for eons. But size isn't even the weird part. The weird part is what it's made of. When the James Webb Space Telescope turned its incredible eyes toward 3I divided by Atlas, it found something that shouldn't exist. At least, not according to everything we thought we knew about how comets form. The chemical composition was completely off. Wrong in ways that made scientists go back and check their instruments multiple times because they couldn't believe what they were seeing. See, normal comets in our solar system are mostly water ice with some other stuff mixed in. Carbon dioxide? Sure, but not that much. Maybe 3% of the comet is carbon dioxide. The rest is mostly water. That's what we expect. That's what makes sense. 3I divided by Atlas has a carbon dioxide to water ratio of 7.6 to 1. Read that again. More than 7 times as much carbon dioxide as water, among the highest ratios ever observed in any comet anywhere. It's so extreme that at first scientists thought there must be an error, but there wasn't. This tells us something profound. This comet didn't form in conditions like anywhere in our solar system. It formed in a place where carbon dioxide dominated, where the temperature and chemistry was so different from what we know that it created something unlike anything orbiting our Sunday. But where? Where in the galaxy would create something like this? The answer is going to blow your mind. Based on its trajectory and velocity, astronomers have traced 3I divided by Atlas back to its origins. And they're pretty sure it came from something called the galactic thick disk. Now, unless you're an astronomer, you've probably never heard of the thick disk. Most people haven't. But understanding what it is makes this whole story even more incredible. Our galaxy, the Milky Way, isn't just a flat spiral like you see in pictures. It actually has layers. There's the thin disk where most stars live, including our Sun. That's where all the action happens, where new stars are being born, where the chemistry is relatively recent. But above and below that thin disk, there's another population of stars. The thick disk. These are ancient stars. Old stars. Stars that formed when the universe was significantly younger, when the chemistry of the galaxy was completely different. These stars orbit above and below the galactic plane, and they're some of the oldest objects in our entire galaxy. 3I divided by Atlas likely came from a solar system in that thick disk. A solar system that formed when the Milky Way was less than half its current age, when the universe itself was younger and stranger than it is today. Think about what that means for a second. This comet is carrying chemical signatures from an era of cosmic history that we can barely study. It's like finding a message written in a language from a civilization that died billions of years ago. Except this message is written in atoms and molecules, frozen in ice, preserved perfectly in the near absolute zero void of space. For 7 billion years, this object has been drifting. 7 billion. That number is hard to even comprehend. Life on Earth has only existed for maybe 3.5 billion years. Complex life, animals, and plants have only been around for about 500 million years. Modern humans, 200,000 years, give or take. This comet has been traveling through space for 35,000 times longer than humans have existed. It's been wandering through the darkness since before our solar system even formed, before the cloud of gas and dust that would become our sun and planets even started to collapse. During those 7 billion years, where do you think it went? What did it see? It probably passed through molecular clouds, those vast regions of gas and dust where new stars are born. It might have witnessed stars being created, watched as fusion ignited in newborn stellar cores, and light flooded into space for the first time. It probably saw those same stars die, maybe even pass through the expanding shells of supernovae, getting bathed in radiation and high-energy particles. That radiation, by the way, is part of why 3I divided by Atlas is so weird chemically. See, when you expose ice to cosmic rays for billions of years in the freezing void of space, something happens. The radiation breaks apart molecules and reforms them into new combinations. It's called radiolysis. And over billions of years, it can cook the surface of a comet, creating new chemicals that weren't there originally. Scientists think 3I divided by Atlas might have what they call a cooked shell, a layer on its surface where eons of cosmic ray bombardment have created additional carbon dioxide and other unusual compounds. The comet's interior might be relatively normal, but its outer layers have been transformed by billions of years of radiation exposure into something completely unique. This is chemistry from the void itself. Chemistry created by time and radiation and the cruel, patient work of cosmic rays in the darkness between the stars. But 3I divided by Atlas didn't stay in the void forever. Something changed. Something pulled it out of its lonely trajectory through interstellar space and sent it here, to us, to our solar system. Probably, it was another star. Comets are so light, so fragile in cosmic terms, that even a distant pass by a star can alter their trajectory significantly. Maybe 3 billion years ago, or 4, or 5, 3I divided by Atlas passed within a few light years of some random star. The gravity from that star gave the comet a tiny nudge, changed its velocity by just a little bit. But a little bit, over billions of years, adds up to everything. That tiny nudge sent 3I divided by Atlas on a new path. A path that, after unimaginable time and distance, would lead it here, to our Sunday. To this moment, the comet is approaching fast. Right now, it's screaming through our solar system at about 58 kilometers per second relative to the Sunday that's hyperbolic velocity. It's going so fast that the sun's gravity can't capture it. This is just a flyby, a brief visit before it continues on its eternal journey through the galaxy. But what a visit it's going to be. In October 2025, just a few weeks from now, as you listen to this, 3I divided by Atlas will reach perihelion. That's the closest point in its orbit to the Sunday. It'll be about 1.36 astronomical units away, just a bit farther out than Earth's orbit. And at that point, it'll be moving at its maximum velocity, 68 kilometers per second, over 150,000 miles per hour. But here's the thing that makes this really interesting, really unprecedented. Before it reaches the sun, it's going to pass very close to something else. Jupiter. In March 2026, 3I divided by Atlas will pass within 0.358 astronomical units of Jupiter. That's about 53.5 million kilometers. Now, I know that sounds far away, and in human terms, it is. That's like 138 times farther than the moon is from Earth. But in cosmic terms, that's incredibly close, dangerously close even. Close enough that Jupiter's immense gravity will definitely have an effect on the comet's trajectory. Close enough that the comet will pass right through Jupiter's magnetosphere. And that's when things might get really weird. See, Jupiter isn't just a planet, it's a magnetic monster. The magnetic field generated by Jupiter is the largest structure in our entire solar system, except for the sun's heliosphere. It extends millions of kilometers into space. On the side facing the sun, it reaches out about 7 million kilometers. On the opposite side, it stretches almost all the way to Saturn's orbit. This magnetosphere is generated by electrical currents deep inside Jupiter, in layers of metallic hydrogen that exist under such extreme pressure that hydrogen stops acting like a gas and starts conducting electricity like metal. These currents create a magnetic field that traps charged particles, creating vast belts of radiation around the planet. It creates auroras at Jupiter's poles that are bigger than Earth. It interacts with Jupiter's moons, especially Io, creating electrical currents that generate radio emissions we can detect billions of kilometers away. It's not just a magnetic field, it's an entire ecosystem of plasma and radiation and electromagnetic forces, constantly churning, constantly active. And 3I divided by Atlas is about to fly right through it. Now, nobody knows exactly what's going to happen when an interstellar comet with such a bizarre chemical composition passes through Jupiter's magnetosphere at such high speed. We've never observed anything like this before. But we can make some educated guesses based on what we've seen in the past. Back in July 1994, something historic happened at Jupiter. A comet called Shoemaker-Levy 9 didn't just pass by Jupiter, it crashed into it. The comet had been captured by Jupiter's gravity on an earlier pass and broken apart into more than 20 fragments. And in 1994, all those fragments, one by one, smashed into Jupiter's atmosphere at incredible speeds. The impacts were spectacular. Each fragment hit with the force of millions of nuclear bombs. They created fireballs bigger than Earth. They left dark scars in Jupiter's atmosphere that lasted for months. Astronomers around the world watched in awe as the most violent impacts in recorded solar system history unfolded in real time. But the impacts did something else too. Something subtle that most people don't know about. They disrupted Jupiter's magnetic field. The violence of those collisions sent shockwaves through Jupiter's atmosphere and magnetosphere. They created new auroras, strange and temporary. They deposited chemicals into Jupiter's upper atmosphere that changed its composition for years. Carbon monoxide, hydrogen cyanide, water vapor, sulfur, compounds. All of these chemicals, vaporized from the comet and the deep layers of Jupiter's atmosphere that were exposed by the impacts, spread through the planet's stratosphere. Some of those chemicals are still there today, more than 30 years later. Jupiter still bears the chemical scars of Shoemaker-Levy 9. Now, 3I divided by Atlas isn't going to hit Jupiter. It's going to miss. But it's still going to come very, very close. And when it does, its plasma tail, the cloud of charged particles that surrounds every active comet, is going to interact with Jupiter's magnetic field. Think of it like this. The comet is surrounded by a cloud of ionized gas, stuff that's been vaporized off its surface by the sun's heat. This gas is electrically charged. And Jupiter's magnetosphere is full of moving magnetic field lines, rotating with the planet every 10 hours. When charged particles meet moving magnetic fields, something happens. Electrical currents start to flow. This is exactly what happens with Io, one of Jupiter's moons. Io is volcanically active, constantly spewing out sulfur and oxygen into space. This material gets ionized and forms a huge donut-shaped cloud around Jupiter called the Io plasma torus. As Jupiter's magnetic field rotates, it drags this plasma along with it, and the interaction creates electrical currents between Io and Jupiter that carry millions of amps of electrical power. These currents generate radio emissions that we can detect on Earth with radio telescopes. 3I divided by Atlas might create something similar. As it passes through Jupiter's magnetosphere, the comet's plasma coma could interact with Jupiter's rotating magnetic field, creating temporary electrical currents. These currents could generate radio bursts. They could create temporary auroras on Jupiter. They could even cause subtle changes in the structure of the magnetosphere itself. Scientists are calling this a potential magnetospheric active experiment. Basically, nature is going to run an experiment for us, showing us what happens when an interstellar visitor meets a planetary magnetic field. And we get to watch. Now, these effects will probably be subtle. We're not going to see giant explosions or anything like that. Jupiter is massive and its magnetosphere is powerful. A small comet, even an interstellar one, isn't going to fundamentally change it, but there might be detectable effects, radio emissions, changes in the particle environment, maybe some unusual auroral activity. And here's the really fascinating part. Some of these effects might not show up immediately. Jupiter's magnetic field is complex and dynamic. The Juno spacecraft, which has been orbiting Jupiter since 2016, has discovered that the magnetic field is far stranger than we thought. There are localized patches of intense magnetic field that drift around the planet over time. There's something called the Great Blue Spot, a region of especially strong magnetic field near the equator that moves at about 4 centimeters per second relative to the planet's deeper interior. The magnetic field is always changing, always evolving, and any perturbation caused by 3I divided by Atlas might not manifest in obvious ways right away. The effects could ripple through the magnetosphere over weeks or months, creating subtle changes that only become apparent when scientists compare detailed measurements from before and after the encounter. This is the kind of science that requires patience, the kind where you have to watch carefully and compare tiny details. But That's what makes it exciting. We're going to learn something new about how magnetospheres work, how comets interact with planetary magnetic fields, how the universe operates at scales we can't directly experiment with. But let's step back for a moment, because there's something even bigger going on here. Something that 3I divided by Atlas might teach us that goes beyond just this one encounter. This comet might hold the key to solving one of the biggest mysteries in planetary science. See, we don't actually understand how planets form. I know that sounds crazy. We live on a planet. There are 8 planets in our solar system. We've found thousands of planets around other stars. Surely we understand how they form, right? Wrong. We've got some good ideas, sure. But there's a major problem with our models of planet formation. A problem that scientists have been struggling with for decades. It's called the meter-sized barrier. Here's the issue. Planets form in disks of gas and dust around young stars. The dust particles, which start out microscopic, bump into each other and stick together through electrostatic forces. They build up slowly, growing from dust grains to pebbles to rocks. So far, so good. The physics makes sense. But then you get to objects about a meter across and everything breaks down. At that size, the physics changes. Meter-sized rocks don't stick together when they collide. They bounce off each other or shatter into smaller pieces. The collision speeds are too high. The objects are too big for electrostatic forces to hold them together, but too small for gravity to pull them together. According to our simulations, planets should never get past this stage. Growth should stall at about meter size, and that should be it. No more planets. Just a disk full of meter-sized rubble orbiting forever. But obviously that's not what happens. Planets do form. We exist. So something is wrong with our models. Some piece of the puzzle is missing. Various solutions have been proposed. Maybe the dust settles into dense clumps where gravity can take over directly. Maybe turbulence in the disk helps concentrate material. Maybe ice helps objects stick together better in the outer parts of the disk. All of these might play a role. But recently, some scientists have proposed a completely different solution. A radical idea that 3I divided by Atlas might actually provide evidence for. The idea is this. What if planets don't form from scratch in protoplanetary disks at all? What if they get a head start? What if interstellar objects, comets, and asteroids wandering between the stars sometimes get captured by protoplanetary disks? These objects are already big, already held together by their own gravity. They've already bypassed the meter-sized barrier. If a young star captures a few of these interstellar objects, they could act as seeds. Gravitational nuclei. Places where smaller dust and pebbles can accrete onto something that's already solid and stable. This would solve the meter barrier problem instantly. You don't need to grow from dust to planet in one continuous process. You start with pre-made building blocks from interstellar space. Objects that have already done the hard work of getting past that problematic size range. Then you just add more material onto them until you have a full-sized planet. It sounds wild, but it might actually be true. And here's why 3I divided by Atlas is relevant. If interstellar objects are common enough, and if they have the right properties to be captured by young stars, then this mechanism could work. But we didn't know if interstellar objects were common until very recently. Oumuamua and Borisov were the first ones we ever detected, and that was only a few years ago. Now we have 3I divided by Atlas. 3 detections in 8 years. And keep in mind, we're only catching the objects that happen to pass close to Earth, and only the ones that are big enough and active enough for our telescopes to spot. For every interstellar object we detect, there are probably thousands or millions that pass through the solar system unnoticed, Too small or too dark or too far away to see. If interstellar space is full of objects like 3I divided by Atlas, wandering between the stars, then young stellar systems must be capturing them all the time. Every million years, a few might wander into a protoplanetary disk and get grabbed by the star's gravity. Over the 10 million years it takes for planets to form, that's dozens or hundreds of captured interstellar objects. More than enough to seed planet formation. And here's the really interesting part. This might explain why higher mass stars tend to have more massive planets. A bigger star has a larger gravitational reach. It can capture interstellar objects from farther away, so more massive stars would naturally capture more interstellar seeds, leading to more and bigger planets. This would also explain why we sometimes find massive gas giant planets around very young stars, stars that shouldn't have had time to form planets through normal processes. If those stars captured a bunch of large interstellar objects early on, those objects could have acted as cores that rapidly accumulated gas from the protoplanetary disk, forming giant planets much faster than usual. 3I divided by ATLAS might be showing us a fundamental mechanism of how solar systems form. Not just ours, but systems throughout the entire galaxy. It's not just a comet. It's a window into the process of planetary birth. But even beyond that scientific significance, there's something poetic about 3I divided by Atlas. Something that speaks to deeper questions about the nature of the universe and our place in it. This object is 7 billion years old. It has been traveling through space for longer than our entire solar system has existed. It has witnessed the birth and death of countless stars. It has drifted through regions of space that we will never visit, never even see. It carries within its frozen structure the chemical memory of a time and place completely alien to us. And now, for a brief moment, it's here, passing through our neighborhood, giving us a chance to study it, to learn from it, to glimpse the ancient history it carries. In a few months, it will pass Jupiter. It will have its moment of interaction with that giant planet's magnetic field. We'll take measurements, we'll watch carefully, we'll learn what we can. Then it will continue on its way toward the sun, swing around perihelion, and head back out into interstellar space. And then it will be gone forever. It will leave our solar system at such a high speed that the sun's gravity will never pull it back. It will drift away into the darkness, continuing its eternal journey through the galaxy. Maybe in another few billion years, it will pass through another star system. Maybe that system will have life, and maybe they'll detect it and study it and wonder about the ancient world it came from. Or maybe it will just drift forever, alone in the void, carrying its 7 billion year memory to nowhere in particular. A message that never gets delivered, a story that never gets told. Except we're telling it right now. We caught it, we saw it, we're listening to what it has to say. There's something profound about that. Something that puts our own existence into perspective. We are creatures that live for decades, maybe a century if we're lucky. We build civilizations that last for thousands of years before they crumble. We think of ancient history as being a few thousand years old. Maybe 10,000 if we're being generous. But 3I divided by Atlas has been traveling for 7 billion years. It's older than our entire planet. It's older than the mountains and the oceans and the atmosphere. It's older than life itself. It predates everything we know and everything we've ever been. And yet, for just this moment, our paths cross. This ancient wanderer and these tiny temporary beings on a small rocky planet have this brief overlap. We exist in the same moment of cosmic time, sharing the same space, looking at each other across the vast distances. Well, we're looking at it anyway. It doesn't have eyes. But you get the point. It makes you think about how interconnected everything in the universe really is. This comet formed in a solar system around a star that might not even exist anymore. That star was formed from gas clouds that were enriched by earlier generations of stars that had already lived and died. Those stars were formed from the primordial gas that emerged from the Big Bang, mixed with heavier elements created in the first supernovae. Everything is connected. Everything has a history that stretches back to the beginning of time. And occasionally, by pure chance, different branches of that history intersect. An interstellar comet meets a young planet with curious beings on it. And for a moment, information flows. The past speaks to the present. This is why astronomy is so powerful. It's not just about cataloging objects in space or calculating orbits or measuring chemical compositions. It's about connecting with deep time, with deep space, with stories that are so vast and so old that they make our own concerns seem tiny by comparison. And yet, those concerns aren't meaningless. If anything, the vastness makes them more precious. We are part of this story. We are participants in the great cosmic drama. For a brief flicker of time, we get to exist and wonder and learn. We get to look up at the sky and see things like 3i divided by Atlas and understand, even if just a little bit, what they mean. That's not nothing. That's actually everything. But let's get back to the practical stuff. Because while the philosophy is interesting, there's real science happening here. Real observations being made. Real discoveries waiting. As I record this, astronomers around the world are watching 3i divided by Atlas with every tool they have. Ground-based telescopes are tracking its position and brightness. Space telescopes like Hubble and Webb are taking spectroscopic measurements, breaking its light into component wavelengths to identify specific chemicals. Radio telescopes are listening for any emissions. Spacecraft in the solar system are being positioned to get the best views possible. The European Space Agency has already announced that their Mars orbiters are going to observe the comet, and the JUICE spacecraft, which is currently on its way to Jupiter, will have a unique perspective on the Jupiter encounter. It won't arrive at Jupiter until 2031, years after 3i divided by Atlas has left. But during the flyby in 2026, JUICE will still be in the inner solar system, and it will be able to observe the comet from a different angle than Earth-based telescopes can. This multi-point observation strategy is crucial. By watching 3i divided by Atlas from different locations, scientists can triangulate its exact position and trajectory. They can see how its coma develops as it gets closer to the sunday. They can measure how much material it's losing and what that material is made of. The chemical analysis is particularly important. The James Webb Space Telescope has already revealed that extreme carbon dioxide ratio, but there's more to discover. Scientists are looking for other unusual compounds. They're measuring isotope ratios, which can tell us about the temperature and conditions where the comet formed. They're looking for organic molecules, complex carbon-based chemicals that might give us clues about prebiotic chemistry in other solar systems. There's particular interest in finding out if 3i divided by Atlas contains any amino acids or other building blocks of life. Previous studies of comets have found amino acids in meteorites that came from comets that hit Earth. If interstellar comets also carry these organic compounds, it strengthens the idea that the ingredients for life might be common throughout the galaxy, delivered by comets to newly forming planets. This is called panspermia, the idea that life or its precursors might spread between worlds on comets and asteroids. It's controversial, but it's not as crazy as it sounds. We know that microbes can survive in space for extended periods. We know that organic molecules can form in interstellar space and survive in comets. If those comets then deliver that material to planets with the right conditions, life could get a head start. Did life on Earth start this way? Maybe, we don't know. But studying comets like 3I divided by Atlas helps us understand whether it's even possible. Another thing scientists are looking for is how the comet's activity changes over time. Right now, 3I divided by Atlas is developing a visible tail as it gets closer to the sun and starts to heat up. The sun's radiation is warming the comet's surface, causing ices to sublimate directly from solid to gas. This gas carries dust particles with it, creating the characteristic tail that makes comets so spectacular. But interstellar comets might behave differently than solar system comets. They've spent billions of years in the incredibly cold environment of interstellar space, where temperatures are only a few degrees above absolute zero. This extreme cold can cause subtle changes in the structure of ice, making it behave differently when it finally gets heated. Also, remember that cooked shell we talked about earlier. The surface layers of 3I divided by Atlas have been processed by cosmic radiation for eons. This might affect how easily the comet outgasses. Maybe the radiation created a crust that makes it harder for gas to escape, or maybe it created especially volatile compounds that sublimate more readily. Scientists are watching carefully to see if 3I divided by Atlas shows any unusual outgassing behavior. There's also the question of the comet's rotation. Most comets tumble as they move through space, their rotation axis wobbling and precessing in complex ways. This rotation affects how the comet heats up and where the outgassing is strongest. If scientists can figure out how 3I divided by Atlas is rotating, they can better model its activity and predict how bright it will get at different times. And then there's the possibility of surprises. Comets are notoriously unpredictable. Sometimes they brighten suddenly as pockets of especially volatile material get exposed. Sometimes they split apart, their fragile structure unable to withstand the stress of heating and outgassing. Sometimes they just fizzle out, running out of active material and going dormant. With an interstellar comet that's already so unusual, anything could happen. It might brighten dramatically as it approaches the sun, becoming visible to the naked eye and putting on a spectacular show. Or it might stay relatively dim and only be visible to telescopes. It might break apart spectacularly, giving us a chance to see its interior structure. Or it might stay intact all the way through its passage and leave the solar system in one piece. We just have to watch and wait and see what happens. That's part of the excitement of astronomy. Nature is always full of surprises. Speaking of surprises, there's one event that already happened that was pretty dramatic. Back in September 2025, just a couple months ago, NASA predicted that a coronal mass ejection from the sun was going to hit 3I divided by Atlas. A coronal mass ejection, or CME, is a huge burst of plasma from the sun's corona, traveling through space at hundreds of kilometers per second. When a CME hits a comet, it's like a cosmic punch. The intense solar wind and magnetic fields carried by the CME interact with the comet's coma, compressing it and potentially creating spectacular visual effects. The comet's tail can get dramatically distorted, bending and twisting in response to the CME's magnetic fields. Scientists were eager to observe this interaction. It's not every day you get to watch an interstellar comet get hit by a solar storm. Telescopes were pointed at 3I divided by Atlas, ready to capture the event. And the interaction did happen, though I don't have the detailed results in the materials I was given. But the fact that scientists could predict this kind of event and prepare to observe it shows how sophisticated our understanding of space weather has become. We can forecast solar storms and predict their paths through the solar system. We can anticipate how they'll interact with comets and planets and spacecraft. This kind of forecasting is actually really important for future space missions. If humans are going to travel beyond Earth, we need to understand space weather. CMEs can be dangerous to astronauts, exposing them to harmful radiation. Being able to predict and track these events will be crucial for keeping people safe in deep space. So even this one observation of a CME hitting an interstellar comet has practical implications for the future of space exploration. Everything connects. Every piece of knowledge builds on the others. Now, let's talk more about Jupiter's magnetic field, because this is where things get really interesting when 3I divided by Atlas makes its close approach. Jupiter's magnetic field is generated deep inside the planet in a layer of metallic hydrogen. This sounds like science fiction, but it's real. Under the immense pressure inside Jupiter, hydrogen gets squeezed so hard that it stops behaving like a gas and starts behaving like a liquid metal. Electrons can move freely through it, just like in copper wire. Jupiter rotates fast, once every 10 hours. This rotation creates electrical currents in the metallic hydrogen layer, and those currents generate the magnetic field. It's essentially a giant dynamo, constantly spinning, constantly generating magnetism. The magnetic field extends far out into space, creating the magnetosphere. And this magnetosphere is not empty. It's full of charged particles, plasma trapped by the magnetic field. Most of this plasma comes from Io, Jupiter's volcanic moon. Io is one of the most geologically active objects in the solar system. It has hundreds of active volcanoes, constantly erupting sulfur and sulfur dioxide into space. This volcanic material gets ionized by sunlight and Jupiter's radiation, becoming electrically charged. Jupiter's magnetic field then captures this ionized material and forces it to rotate along with the planet. This creates the Io plasma torus, a donut-shaped cloud of ionized sulfur and oxygen that surrounds Jupiter at Io's orbital distance. As Jupiter rotates, it drags this plasma along with it, and the interaction generates electrical currents between Io and Jupiter. These currents carry millions of amps of electrical power. They create auroras at Jupiter's poles and generate intense radio emissions. The whole system is incredibly dynamic. The plasma is constantly moving, constantly interacting with Jupiter's magnetic field. And when objects pass through this environment, they can disturb it in interesting ways. When 3I divided by Atlas passes through Jupiter's magnetosphere in March 2026, it will be surrounded by its own plasma, the ionized gas that makes up its coma and tail. This plasma will interact with Jupiter's rotating magnetic field. Electrical currents might form, similar to what happens with Io. These currents could generate radio emissions that we could detect on Earth. The Juno spacecraft, which is still orbiting Jupiter, will be perfectly positioned to observe these effects. Juno has instruments designed to measure magnetic fields and detect charged particles. It can measure radio emissions. It can watch how the magnetosphere responds to perturbations. Juno has already made some incredible discoveries about Jupiter's magnetic field. Before Juno, we thought Jupiter's magnetic field was relatively simple, a basic dipole like Earth's field but much stronger. Juno showed us that it's far more complex. There are localized regions where the field is much stronger than expected. There are areas where the field is weaker. The field is not symmetric, it's lumpy and irregular. And most surprisingly, these irregularities are not static. They move over time, drifting eastward relative to the planet's deep interior. The Great Blue Spot, for example, is a region near Jupiter's equator where the magnetic field is especially strong. It's been drifting eastward at about 4 centimeters per second for years now. Scientists think this drift is caused by winds deep in Jupiter's atmosphere, in the layer where the magnetic field is generated. These winds drag the magnetic field lines along with them, creating the observed drift. All this complexity means that predicting exactly how Jupiter's magnetic field will interact with 3I divided by Atlas is difficult. The encounter will happen in a specific region of the magnetosphere, and the local conditions there will determine what effects we see. If 3I divided by Atlas passes through a particularly active region, we might see dramatic effects. Strong electrical currents, bright auroras, intense radio emissions. If it passes through a quieter region, the effects might be subtle, but even subtle effects would be valuable scientifically. Any measurement we can make of how a comet interacts with a planetary magnetosphere helps us understand these complex systems better. And remember, this is not just academic curiosity. Understanding magnetospheres is important for space weather forecasting, for protecting satellites and spacecraft, and for eventually sending humans to other planets. Mars, for example, lost most of its atmosphere over billions of years because it doesn't have a strong magnetic field to protect it from the solar wind. Understanding how magnetospheres work and how they interact with the solar environment could help us figure out how to protect future Mars colonies from radiation. So when 3I divided by Atlas passes Jupiter in a few months, scientists will be watching very carefully. They'll be measuring everything they can: magnetic field strength and orientation, particle densities and energies, radio emissions at various frequencies, auroral activity, changes in the plasma torus, everything. And they'll compare those measurements to measurements taken before the encounter to see what changed. They'll look for patterns and correlations. They'll build models to try to explain what they observe. And all of that work will contribute to our understanding of how the universe works at scales we can't directly manipulate. This is what science is really about. Not just answering questions, but learning how to ask better questions. Every observation leads to new mysteries, new puzzles to solve. And speaking of mysteries, there's something else about 3I divided by Atlas that scientists are really curious about. Its nucleus, the solid core of ice and rock at the center of all that gas and dust. We don't actually know what the nucleus looks like. Not yet. It's too small and too far away to image directly with our current telescopes. Even Hubble can't resolve it into anything more than a point of light surrounded by the fuzzy glow of the coma. But scientists have ways of estimating the size. They measure how much light the comet reflects. They measure how much gas and dust it's producing. They use models of how comets behave to work backward from those observations to figure out how big the nucleus must be. The current estimates suggest 3I divided by Atlas has a nucleus several kilometers across. Maybe 3 kilometers, maybe 5, maybe more. That's big for a comet. Most comets are only a kilometer or 2. Really big comets like Hale-Bopp are maybe 40 kilometers across, but those are rare. If 3I divided by Atlas really is several kilometers wide, it's got a lot of mass, a lot of material, which makes sense if it's been surviving in interstellar space for 7 billion years. Smaller comets might get eroded away by cosmic rays and collisions with dust grains over such enormous timescales. You need to be big to survive that long. But here's what's really interesting. The nucleus probably isn't a single solid chunk of rock. Comets are more like loosely packed snowballs. They're made of lots of smaller pieces held together by gravity and ice, with lots of empty space in between. Scientists call this structure a rubble pile. This rubble pile structure makes comets fragile. They can break apart easily if they get too close to a large gravitational source or if internal stresses from outgassing get too strong. We've seen it happen. Several comets have broken apart while passing close to the Sun or Jupiter. Could 3I divided by Atlas break apart during its Jupiter flyby? Maybe. The gravitational stress from passing so close to Jupiter's enormous mass could potentially pull the comet apart if its internal structure is weak enough. Scientists call this tidal disruption. When a comet gets close to a massive object, the side closer to that object feels stronger gravity than the side farther away. This difference in gravitational pull creates tidal forces that try to stretch the comet. If those forces are stronger than the comet's own gravity holding it together, the comet breaks apart. Jupiter has disrupted comets before. That's what happened to Shoemaker-Levy 9. On an earlier pass by Jupiter, the tidal forces pulled it into more than 20 pieces. Those pieces then came back on the next orbit and hit Jupiter. Will that happen to 3I divided by Atlas? Probably not. It's not passing quite as close as Shoemaker-Levy 9 did, and it might be large enough and strong enough to hold together. But there's a chance. And if it does break apart, that would actually be scientifically fascinating because it would give us a look at the comet's interior structure. When comets break apart, we get to see layers that were previously hidden. We can study the composition of material that's been buried under the surface for billions of years. We can see if the interior is different from the surface. We can watch how the different pieces behave as they separate and develop their own comas and tails. So, scientists will be watching carefully for any signs that 3I divided by Atlas is coming apart. Small fragments breaking off, changes in the brightness or shape of the coma, multiple tails forming. Any of these could indicate that the nucleus is fragmenting. But even if it stays intact, there are other things to look for. Outbursts, for example. Sometimes comets suddenly brighten when a pocket of especially volatile ice gets exposed and rapidly sublimates. These outbursts can make a comet dozens or even hundreds of times brighter in a matter of hours or days. Interstellar comets might be particularly prone to outbursts because their surfaces have been processed by radiation for so long. That cooked shell might be sealing in pockets of pristine ice underneath. If cracks form in the shell as the comet heats up, those pockets could suddenly vent to space, creating a dramatic outburst. 3I divided by Atlas has already shown some signs of activity. It became visible earlier than expected, brightening while still beyond Jupiter's orbit. This suggests it has some particularly volatile material that can sublimate even in the weak sunlight of the outer solar system. As it gets closer to the sun, it will heat up more. The outgassing will intensify. The coma and tail will grow. It might become visible to amateur astronomers with decent telescopes. It might even become a naked eye object if it gets bright enough, though that's probably unlikely given its trajectory. But you never know with comets. They surprise us all the time. And an interstellar comet that's already shown unusual chemistry might have more surprises in store. There's also the question of what happens after 3I divided by Atlas leaves our solar system. Where will it go next? Will it ever encounter another star system? Based on its trajectory and velocity, astronomers can calculate its future path through the galaxy. It will leave our solar system moving at about 58 kilometers per second relative to the sun date, but the galaxy as a whole is rotating, and 3I divided by Atlas will be caught up in that rotation. It will orbit the galactic center along with hundreds of billions of other stars and countless other objects. Its orbit will take it above and below the galactic plane, through the thick disk where it probably originated. It might pass through giant molecular clouds, regions where new stars are forming. It might come close to massive stars whose radiation and stellar winds could erode more material from its surface. It might even pass through the expanding remnants of supernovae, getting bathed in high-energy particles and heavy elements created in the explosion. And eventually, maybe billions of years from now, it might pass close to another star. That star's gravity might capture it, pulling it into an orbit, or it might just bend its trajectory slightly, sending it off in a new direction. The universe is vast, and time is long. Almost anything can happen given enough time and space. 3I divided by Atlas will wander through the galaxy until some chance encounter changes its fate. Maybe it will be captured. Maybe it will be destroyed in a collision. Maybe it will just drift forever, an eternal wanderer carrying its 7 billion year memory through an endless cosmic night. There's something melancholy about that thought. This ancient object, older than our entire world, traveling alone through the darkness for spans of time we can barely comprehend. No destination, no purpose, just eternal motion through an uncaring universe. But then again, maybe that's not the right way to think about it. Maybe there's something beautiful in that endless journey, something pure. 3I divided by Atlas doesn't need a purpose. It doesn't need to arrive anywhere. It just exists, moving through space and time, a tiny fragment of an ancient world preserving memories of a place and time that no longer exist. And for one brief moment, it intersects with us. We get to see it, study it, learn from it. We get to connect with that ancient past, to touch something that predates everything we know. That's a gift, really. A rare moment of connection across the vast scales of space and time that usually keep different parts of the universe separated. We should appreciate it while it lasts, because soon enough, 3I divided by Atlas will be gone. It will pass Jupiter, swing around the sun, and head back out into the dark. Within a few years, it will be beyond the orbit of Neptune, too faint and too far for our telescopes to see. Within a few decades, it will cross the boundary of our solar system and enter true interstellar space once again. And we'll never see it again. It will disappear into the cosmic ocean, one more unnamed wanderer among countless others, invisible and unreachable. Unless, of course, we send something after it. And that's actually not as crazy as it sounds. There have been proposals for interstellar probe missions, small, fast spacecraft that could be sent to intercept and study interstellar objects. The technology is challenging, but not impossible. You'd need a spacecraft that could accelerate to very high speeds, tens of kilometers per second. You'd need it to be autonomous, able to navigate and make decisions without real-time communication with Earth. You'd need instruments that could study the object during a high-speed flyby lasting just minutes or hours. It would be expensive and risky, but it would be worth it. Think about what we could learn from a close-up study of an interstellar comet. High-resolution images of the nucleus, direct sampling of the coma to analyze its exact composition, measurements of the magnetic field and plasma environment around the comet, data on the surface structure and how it's changed over billions of years. We could answer so many questions. What does a comet look like after 7 billion years in space? How deep is that radiation-processed crust? What's the interior structure? Are there organic molecules that might give us clues about prebiotic chemistry? Could we detect any amino acids or other building blocks of life? Some scientists have proposed that we could even bring samples back to Earth. A sample return mission from an interstellar object would be incredibly challenging, but the scientific payoff would be enormous. We could study material from another solar system in laboratories on Earth with instruments far more sophisticated than anything we can send into space. Imagine holding a piece of rock that formed 4 or 5 or 7 billion years ago in a solar system light years away from ours. Imagine analyzing its isotopes and minerals and organic compounds, reading the chemical story of a place and time completely alien to us. That's the kind of science that could revolutionize our understanding of the universe, and it's not completely out of reach. We have the technology to do it, or at least to start working toward it. We just need the will and the funding and the long-term commitment. Maybe 3i divided by Atlas will be the inspiration that drives that effort. Maybe its brief visit to our solar system will convince enough people that this is worth doing. That understanding our place in the universe is worth the investment. Or maybe not. Maybe 3i divided by Atlas will come and go, studied intensely for a few months, and then largely forgotten as the next cosmic mystery captures our attention. That's often how it goes in astronomy. There's always something new to look at, always a new puzzle to solve. But even if 3i divided by Atlas fades from public consciousness, it won't fade from the scientific record. The data we collect from it will be analyzed for years, maybe decades. Papers will be written, theories will be proposed and tested. Debates will rage about what its chemical composition really means and where it truly came from. And that data will join the vast accumulation of knowledge that humanity has been building for centuries. Each observation, each measurement, each discovery adding to the picture. Slowly, piece by piece, we're figuring out how the universe works. It's a long process, a slow process, but it's happening. Every generation adds to what the previous generation discovered. We stand on the shoulders of giants, as the saying goes. Newton and Galileo and Kepler and Copernicus and all the others who came before us, building the foundation of astronomy and physics. And we're building on that foundation, adding new stones, reaching higher. Someday, maybe centuries from now, maybe millennia, future humans will look back at this era and see it as primitive. They'll laugh at how little we knew, how crude our instruments were, how many mistakes we made. But they'll also see that we tried, that we looked up at the sky with curiosity and wonder, that we built telescopes and spacecraft and devoted our lives to understanding the cosmos, that we asked questions and sought answers even when the answers were hard to find. And they'll see that we documented objects like 3i divided by Atlas, that we studied them carefully and preserved the data for future generations, that we contributed our small part to the great ongoing project of understanding reality. That's what this is really about. Not just 3i divided by Atlas specifically, but the larger endeavor of science and knowledge and curiosity. The drive to know, to understand, to connect with something larger than ourselves. Every time we point a telescope at the sky, we're participating in something profound. We're reaching across space and time to touch ancient light, to decode messages written in electromagnetic radiation, to piece together the story of the cosmos. And the cosmos has quite a story to tell, a story of birth and death, of creation and destruction, of incredible violence and delicate beauty. A story that includes 3i divided by Atlas and Jupiter and our sun and Earth and us. We're part of this story. We're not separate from the universe, looking in from the outside. We are the universe looking at itself. We are made of star stuff. As Carl Sagan famously said, the atoms in our bodies were forged in stellar furnaces billions of years ago. We are literally made of ancient stardust, animated by evolution, contemplating our own origins. That's pretty amazing when you think about it. The universe gave rise to complexity and life and consciousness. And now, consciousness is trying to understand the universe that created it. We are the universe's way of knowing itself. 3i divided by Atlas is part of that story too. It's a piece of the puzzle, a fragment of cosmic history that we get to examine and learn from. It connects us to deep time and deep space, to to places and eras far removed from our everyday experience. When you look at it that way, even a lump of ancient ice and rock becomes profound. It's not just a comet. It's a bridge between worlds, a messenger from the past, a physical link to the vast interconnected web of cosmic evolution. And in March 2026, that messenger is going to pass by Jupiter. Two objects, each with their own ancient history, will have a moment of interaction. Energy and matter and electromagnetic forces will flow between them. Changes will occur, subtle but real. And we'll be watching, recording, analyzing, learning. That's what makes this exciting. Not just the spectacle of it, though that's cool too, but the opportunity to learn something new, to add another piece to the puzzle, to understand just a little bit more about how this strange and beautiful universe works. Will the interaction between 3I divided by Atlas and Jupiter reveal secrets about magnetospheres? Maybe. Will it tell us something about planet formation? Possibly. Will it give us clues about the chemistry of ancient solar systems? Probably. But even if it doesn't answer those specific questions, it will definitely teach us something. Every observation does. Every measurement adds data. And that data, combined with all the other data we've collected over the years, slowly builds a picture. Science doesn't usually progress in dramatic leaps. It's not like in the movies where one discovery suddenly explains everything. It's more like assembling a jigsaw puzzle. Each piece adds a little bit to the image. You don't know what the full picture looks like until you've got most of the pieces in place. 3I divided by Atlas is one piece of that puzzle. An important piece because it's so unusual and because it connects to so many different questions. But still, just one piece among thousands or millions. The picture we're assembling is immense. It's the picture of how the universe works, from the smallest quantum scales to the largest cosmic structures. From the first moments after the Big Bang to the far future, when the last stars burn out. From the formation of atoms to the emergence of consciousness. It's an ambitious project, maybe impossibly ambitious, but that's what makes it worth doing. The fact that it's hard, that it requires cooperation across generations and cultures, that it demands our best thinking and our most careful observations. This is humanity at its best. Looking outward, asking questions, seeking truth. Not for profit or power or glory, but simply because we want to know. Because we're curious. Because understanding the universe feels important and meaningful, even if it doesn't put food on the table or solve immediate practical problems. Of course, science does solve practical problems too. The technologies we develop for astronomy often find applications in medicine and communication and countless other fields. The GPS system relies on Einstein's relativity. MRI machines use quantum physics. The internet was developed partly to share data between research institutions. So even the most abstract scientific questions can lead to practical benefits. But that's almost beside the point. We don't study interstellar comets because we think it will lead to new products or economic growth. We do it because it's fascinating, because it feeds something deep in the human spirit. That need to understand, to make sense of the world around us, might be one of the defining traits of our species. Other animals are intelligent, sure, but do they look at the stars and wonder where they came from? Do they try to build models of reality and test them against observation? Maybe some do, in their own way. We don't really know what goes on in the minds of dolphins or elephants or crows, but humans have definitely taken this curiosity thing to an extreme level. We can't help ourselves. We see a mystery and we have to solve it. 3I divided by Atlas is a mystery. An ancient, frozen, chemical mystery traveling through our solar system at absurd speeds. And we're going to solve it, or at least solve parts of it. We're going to figure out where it came from and what it's made of and how it interacts with Jupiter's magnetic field. And then we'll move on to the next mystery. Because there's always another mystery. The universe is full of them. But for now, for this moment, 3I divided by Atlas has our attention. It's the mystery du jour, the puzzle we're focused on. And over the next few months, as it approaches Jupiter and then the Sun, we're going to learn everything we can from it. The encounter with Jupiter in March is going to be particularly interesting, not just because of the potential magnetic interactions, but because it's a genuinely rare event. Interstellar objects passing this close to Jupiter? That probably doesn't happen often. Maybe once every few thousand years, maybe less. We're incredibly lucky to be alive at the right time to see it. If 3I divided by Atlas had passed through our solar system 100 years ago, we wouldn't have had the technology to detect it or study it. 100 years from now, it will be long gone, unreachable, just a footnote in history books. But we're here now, right at the perfect moment, with telescopes powerful enough to see it, and spacecraft positioned to study it, and scientists who know how to interpret the data. That's not just luck, by the way. It's also the result of decades of investment in astronomy and space exploration. The result of thousands of people dedicating their lives to building better instruments and developing better theories and training the next generation of researchers. Science is a collective endeavor. No one person or even one generation can do it alone. It requires continuity, institutions, funding, education. It requires a society that values knowledge and is willing to invest in discovering it. We're fortunate to live in a time and place where that's possible, where we can build space telescopes and planetary missions and radio arrays, where young people can study astronomy and physics and pursue careers in research, where the public is interested enough in cosmic mysteries that they'll read articles or watch videos or listen to recordings about things like interstellar comets. That engagement matters. Public interest drives funding, drives research, drives discoveries, drives more public interest. It's a virtuous cycle, and it's important to keep that cycle going, to keep people excited about science and space and the big questions about the universe. That's partly why events like 3I divided by Atlas are valuable even beyond their immediate scientific importance. They capture the imagination. They remind people that the universe is weird and wonderful and full of surprises. They inspire the next generation of astronomers and physicists and engineers. Some kid right now is reading about 3I divided by Atlas and thinking, wow, that's so cool. I want to study comets when I grow up. And maybe that kid will become the scientist who figures out how to launch a sample return mission to an interstellar object, or who discovers something completely unexpected that revolutionizes our understanding of planet formation. You never know where inspiration will lead, but you have to plant the seeds. You have to show people what's possible, what's out there, what mysteries are waiting to be solved. 3I divided by Atlas is one of those seeds. A small thing in cosmic terms, just a chunk of ice and rock a few kilometers across. But potentially the spark that ignites curiosity in someone who will go on to do great things. That's how science progresses. Not just through formal research and publications, but through inspiration and wonder and the simple joy of learning something new about the universe. And there's definitely joy in this. Joy in understanding that this ancient visitor has been traveling for 7 billion years and finally arrived here, at this place, at this time. Joy in knowing that we can measure its chemistry and track its path and predict its future. Joy in the sheer audacity of pointing our instruments at a speck of light billions of kilometers away and extracting information from it. We live in an age of miracles, really. The ability to study interstellar objects would have seemed like magic to people just a few generations ago. Hell, the very concept of interstellar space would have been incomprehensible for most of human history. But now we know. We know the Earth orbits the Sunday. We know the Sun is one of hundreds of billions of stars in the Milky Way. We know the Milky Way is one of trillions of galaxies in the observable universe. We know the universe is expanding and aging and evolving. And we know that space between the stars isn't truly empty. It's full of objects like 3I divided by Atlas, wandering through the darkness, carrying stories from ancient worlds. That knowledge is precious, hard-won through centuries of observation and thought and debate and refinement. We shouldn't take it for granted. We should celebrate it and build on it and pass it on to future generations. And we should remember that for all we've learned, there's still so much we don't know. Every answer raises new questions. Every discovery opens new mysteries. Why is 3I divided by Atlas's chemistry so unusual? We have theories, but we don't know for sure. Will it interact with Jupiter's magnetosphere in detectable ways? Probably, but we won't know the details until it happens. Will it break apart under tidal stress or stay intact? We'll have to wait and see. And bigger questions remain. How common are interstellar objects? How many are passing through our solar system right now that we haven't detected? Do they really play a role in planet formation? Could they have delivered organic compounds that contributed to the origin of life on Earth? We don't know, not yet, but we're working on it. Observation by observation, measurement by measurement, theory by theory. That's the beauty of science. It's never finished. There's always more to learn, always deeper to go, always another layer of understanding to uncover. 3I divided by Atlas is giving us one of those layers. One more piece of the puzzle. One more glimpse into the workings of the cosmos. And in March 2026, when it makes its closest approach to Jupiter, all eyes will be on it. Professional astronomers with their massive telescopes, amateur astronomers with their backyard setups, space agencies with their spacecraft, science communicators with their cameras and microphones, ready to share the story with the world. We'll watch as this ancient wanderer, this 7-billion-year-old messenger from a dead solar system, passes by the giant of our solar system. We'll measure and record and analyze. We'll compare predictions to observations. We'll be surprised by some things and confirmed in others. And then, after it swings around the sun and heads back out into interstellar space, we'll compile all that data. We'll write papers and give talks and debate interpretations. We'll update our models and refine our theories. We'll add 3I divided by Atlas to the catalog of known interstellar objects and move forward with slightly more knowledge than we had before. That's how progress happens. Slowly, incrementally, but surely. And someday, maybe not in our lifetimes, but eventually, we'll understand the universe well enough to answer all those big questions. Where did we come from? How did life begin? Are we alone? What's the ultimate fate of everything? Those answers are out there, hidden in the cosmic data, waiting to be discovered. Objects like 3I divided by Atlas are part of finding them. Every interstellar visitor brings new information, new clues, new pieces of the puzzle. We just have to keep watching, keep measuring, keep thinking, keep asking questions. Because in the end, that's what makes us human. Not just our intelligence or our technology, but our curiosity, our drive to understand, our refusal to accept mystery as the final answer. We see something strange in the sky and we point our instruments at it. We detect unusual chemistry and we try to explain it. We notice patterns in relationships and we build theories to account for them. That's our nature. That's what we do. And 3I divided by Atlas, this ancient frozen messenger from beyond, gives us one more chance to exercise that nature, to satisfy that curiosity, to learn something new about the universe we inhabit. So as you listen to this, know that something incredible is happening right now. Above your head, through the darkness, a visitor older than our entire world is racing toward the sun. In a few months, it will pass Jupiter and potentially create effects never before observed in human history. Then it will continue on, heading back out into the cosmic dark, its brief visit to our neighborhood complete. And we'll have learned from it, we'll have grown from it, we'll have added its story to our collective understanding of how the universe works. That's not nothing, that's actually everything. Because understanding is what we're here for. It's what gives our brief flicker of existence meaning and purpose. We are part of something vast and ancient and ongoing. We are participants in the great cosmic story. And for just a moment, just this fleeting instant in cosmic time, we get to witness something special. An ancient wanderer, a magnetic giant, a meeting of histories separated by billions of years, all converging here, now, in this moment we share. Make sure you watch for the next video about what actually happens when 3I divided by Atlas meets Jupiter.